So we're going to need to use the Cartier operator to prove the to two notions of ordinarity. So recall that we have this absolute Frobenius from y to y, and we can take the push forward of the de Rham complex here. So let's take f to be f abs. So this absolute Frobenius. This is just the Pth power map on things, and so we have this dude here, y, and this could be all relative to k. I'm just not going to write the k. And then this is f star omega y to the k. And let's say it's so we're doing with a Abelian variety. So I guess I'll do it with g-dimensional here, 0, and then we have these bi's, which is going to be the image of the D map from f star omega I minus 1 to f star omega I, and zi, which is going to be the kernel of the one that goes from I to I plus 1. And then we have this exact sequence, of course, zi2, and then I'm going to call this h I relative of this this complex here, and this goes to 0, and then okay, and so the Cartier operator says that for y smooth, we have so there exists a map here from this hi of here over k. So we had some base, so maybe I'll put the base in. So we're doing it for over a perfect field c of x, so 2 omega y over k. Okay, and so this is inverse of the Frobenius linear. Of the Frobenius linear. So sometimes people call this p minus 1 linear. Okay, so we have this Cartier operator, and we have the inverse of the Cartier operator, and okay, and so I need to define now what so we have this for each one we actually have this C inverse of oh, this is a y here, y from so omega 1 of y to h, so we can do this for i's, f star omega I of y, like so. So this is zi over bi, and then we can using this we can define, so definition, so this the logarithmic derivatives as the kernel of 1 minus cy inverse here, and so this has this gives us a sequence here. Like so, and there's a theorem, and so this is in 4.2 of Lazou's paper, that this thing here is locally generated by forms of the form dy 1 over y1 wedge, and then all the way up to dyi over yi, and then these yi's are invertible. Okay, so there's kind of this description of why it's called a logarithmic derivative. So these look like logarithmic derivatives. I wanted to make a little remark about how to go in between the absolute and relative Frobeniuses, the absolute and relative versions of the Cartier operator, to go between the absolute and relative versions of the Cartier operator. We're just going. You just need to use. You use these two identities here. In that. Okay, so that's one thing I just wanted to say. All right, so and so I can define a notion of ordinarity. So let me give a definition. Y is ordinary if we have vanishing of certain cohomology. So for these hi, y, and then we take the jth one of these is 0. And then here I need to look real quick. So for j, so this is true for j bigger than or equal to 0, and or sorry, j strictly bigger than 0, and I bigger than or equal to 0. Okay, so this is what it means to be ordinary. So there's this. There's also another special version of ordinary. So there's a certain special case of abelian varieties. Okay, and so I'm gonna give like another definition of ordinary. Well, actually, let me just say this. So let me actually define what P rank is. So it turns out that so if A is an abelian variety, over K. So this is going to be again a perfect field of characteristic P. So we know that we can take A and then we can look at its P torsion. Okay, so this is the kernel of multiplication by P, and then we can look at its the points in the algebraic closure, and this is going to be isomorphic to Z mod P to some power here. This thing here, RP of A, so this is called the P rank of A. And it'll turn out that RP of A, well, this is a number in between G and 0. And at this end, this is what we call, this is another version of, this is what will end up being ordinary. So this will be the same thing as ordinary. So when it has maximal P rank. So this is the definition of the P rank. To explain this, you need to explain how the multiplication by P decomposes, and I might do this in another video, but and if I do, I will link to it. Okay, so we have this thing, and it's a number between 0 and G. It turns out this is a fact. And okay, so now I want to say something. I want to prove something. So proposition. So let's take A over K in abelian variety. So the thing that I want to prove is that HI A Bj is equal to 0 for so then let's see what I always forget. So for all I bigger than or equal to 1, or all I bigger than or equal to 0, and all j bigger than 0, if and only if the P rank of A is G. G is going to be the dimension again. G is the dimension of A. Okay, so this is what we have. I want to prove a lemma. So let's say y over k is a smooth projective variety over a perfect field and characteristic field, perfect field and characteristic P. Then I'm going to prove that the following, that two things. I want to prove two identities. The first identity I want to prove is that h1 of y of k bar zp is isomorphic to HOM of maps from the p torsion to zp. Okay, so this thing is actually going to give us the p rank. And then the second thing I wanted to show is that h0 of y omega 1 y log. So these logarithmic derivatives is actually the p torsion of the Picard variety. So I want to prove these two things. Okay, so to prove these, let's look at the first one. So we need some identities. So let's talk about the proof of okay. So there's kind of some fundamental relations for the Cartier operator. So this is so some fundamental sequences from the Cartier sequences. So this is kind of a lemma within a lemma. They are the following. First, we can take so OX to the P, and stick this inside OX, and then take the logarithmic derivative, and here we'll take, and then we have C of X inverse minus 1. Okay, so this is maybe too much information here. I just wanted to write them down for completeness. We're just going to need this one here, and we're going to use this to get our logarithmic differentials out. So let me just copy this one down again. So we have this. Let me do it with y. I'll do it with y's now. And then we have this thing, y. Okay, so since this is exact, we can truncate this. So, and then I'm going to stick this, I'm going to assume that raising to the pth power is going to be injective. So we have this y like this. So this is going to be multiplication by p for this group here. And then this goes to the kernel of this map. And this is exact now. And this thing is by definition omega 1 y with the logarithmic differentials. And so now these tell us how the two things are related. And now we can take cohomology. So taking cohomology gives us the following. It gives us H0 H0. Okay, and then the next row is H1 to H1 like this, and so this is multiplication by p here, and it goes on. Okay, so again, now is where we're going to use the assumption that y is proper. So y is proper, this means that this becomes k star, and this becomes a k star. And then since k is perfect, this becomes surjective. Okay, so then the image of this is the whole thing, and the whole thing's the kernel of the next thing. So then this becomes exact here. Okay, and then we replace this one by a kernel. Okay, so this tells us that we get 0 goes to h0 omega y log. And then we went to the next row here. The next row actually becomes, we just replace that with a kernel, p. So this is the kernel of the multiplication map here. And then we have that this is a isomorphism. Okay, so this implies that. Okay, so we have this piece. All right. I'm going to prove now, or I'm going to kind of explain why so if y is an abelian group, or abelian scheme, abelian variety over k, then we're going to show this thing. Okay, we're going to do this. Okay. And so to do this, I want to make some... so I think the idea is the following. So we're going to use the sequence here where you take... and we'll take here the kernel of multiplication by p. This is multiplication by p, like so. And then we'll apply the following functor to get the following sequence. So I think we get here, we get, okay, so this is contravariant. So now we're going to get, so here, okay, crap, so p so then here we get yk bar z mod p, and then we go again, like so, and then and so on and so forth. Okay, and so this map here is what you get from multiplication. So let's call this map alpha, and then let's call this map or let's call this thing. Okay, so there's two things that we want to show. It suffices to show from this sequence. Okay. It suffices to show that hom yk bar, this is 0, and that the image of, so that the alpha of k mod p. Okay, so that so that when we replace by the kernel of this, that we get the whole thing. And then this, so that would get rid of this, and that would get rid of, well, essentially this after replacing by a kernel. And then it would show that those two things are isomorphic. Okay, and so remember that alpha here is really h1 of multiplication by p of z mod p. Okay, I claim, so the claim, I think this is how it works. I think I convinced myself that here, so this thing, so if you, this is group cohomology. With a trivial action, and abelian groups, lets us check that, let's call this 1 and 2, 2 directly. Okay, and then the second part here, or the first part, I think the idea is the following. The idea of 2, of 1, is that, well, okay, so here's what happens. So y of k bar, okay, so this is like, and this doesn't mean anything precise, c to the g mod a lattice, right? Here, so here we're looking for Homs from this thing into z mod p. Okay, so this is like a Hom from here to here. But here, we could have actually z mod p. Well, this thing is, you can take something from c to the g to here, and there's actually no maps. The only maps from here to here are 0. This is always the 0 map. Okay, since this is always the 0 map, that means this has to be the 0 map. Okay, so if we could write this as the quotient of something, this would be okay. And actually, this is really bad, right? So this map here is already really bad. The map sends everything that's not p torsion all non-p torsion stuff to 0. Okay, so it's believable that these two things are 0, which would show the proof. Okay, so this is the idea, I think. Okay. All right, so I'm going to stop here and then continue in a second. So I'm going to state a lemma that I'm going to use but not prove. So here's the idea. So here's a lemma. I call this the Bloch-Kato lemma. Okay, and so this actually is in their paper, P-Kato cohomology. This is page 138. Okay, in section 7.1. Okay, and so it says that if we're working over an algebraically closed field, so this is where this algebraically closed field hypothesis comes in. It says that if you fix, so there's kind of two things. You have this vanishing, the ordinarity condition, which says that hi y, so y is any variety, so y is just a scheme over k. Okay, and it says that if you have this vanishing, so this statement here, for all I, okay, so this vanishing, and it depends on j, okay, so this thing, under this hypothesis, you have one thing, you have that this map is, you have a certain map is injective. The map that you have that's injective is these guys here, log, here, into the other thing that you have, so this is injective. Okay, we call this phi. If phi is bijective, this is true if and only if you get the next level of vanishing here. So you'll get this hypothesis that that h I y b j plus 1 is equal to 0, and this is for all I. Okay, so one of the things that you'll do is we'll take this condition, and then we'll get that this map's injective. Okay, well then after counting here, so maybe we'll count that these have the same dimension, then that'll show that this is bijective. Once we have its bijective, then we get this next step, and that's how the proof for the ordinarity will work, and that's how they've cooked it up. So this is kind of key to their induction argument, to show that the ordinarity here is the same thing as ordinarity in the case for abelian varieties. So I'm going to show that P rank ordinarity implies the Bloch-Kato ordinarity. Okay, so suppose the P rank of this abelian variety is the dimension, and then we get for free, since b0 is 0, this implies that hi of y of b0 is 0 for all y, so for all I. Okay, and this thing here, under these conditions, this tells us that that this map here, the Bloch-Kato lemma says that here to h 0, so hi y omega 0. So this is injective here. We also have that, okay, so this is true. And we also can count dimensions on either side of this. So how do we count dimensions? So we know that we have this formula. This is equal to the dimension y log. Okay, and we also know that this is equal to, by the hypothesis, so these are the same dimension, which implies that this map's an isomorphism. Okay, so now that we have this as an isomorphism, okay, so now we apply Bloch-Kato again. Says that if this map here so this is for all I, so this implies that hi y omega 1 y, oh sorry, b1 y is 0 for all I. Okay, so we went from the 0th step. So we went from the 0th step here, and the 0th step we get for free. Using this hypothesis, we got the 0th step gives us this injectivity. Then, using the hypothesis here, we are allowed to show that we can show that this is an isomorphism. Using that this is an isomorphism allows us to apply the second part of the Bloch-Kato lemma, which tells us that we now have an this isomorphism, and that's that this isomorphism implies vanishing. Okay. Okay, and so now we got to do it again. Okay, so now by Bloch-Kato, Kato part 1, well, this vanishing here tells us that this map here omega 1 is into I, y here. So we have this here. And now we're going to do the same thing again. Now we want to do, so that now we need to dimension count. And show in order to apply Bloch-Kato 2 again. Okay, so let me tell you how the dimension count works. Okay, so the dimension count for every one of these, so what we'll do is we'll do HIY omega JY. Okay, this is one thing that we need to count, and then we need to count this thing, J. Okay, so how do you count this? So this thing actually looks like HIYO tensored with H0 at Y omega JY, like this. Okay, and then there's this kind of just a general fact about abelian varieties. So this is, like, for example, found in Mumford, that this thing is isomorphic to this. So as so this is a ring where you have a cup product, and this is, you have this wedge product here, and this thing is the same thing. This is H0Y omega 1Y, like so. Okay, and so this happens J times, and this happens I times. And I think the same thing happens here. So here we have HIYO H, so I should probably put isomorphisms here. H0Y omega JY log, like so. And then this becomes isomorphic to the highest wedge power of H1YO tensor, and then this is the highest wedge power here, H0Y omega 1Y log. Okay, and then so this is the one thing I'm a little shaky on, is this isomorphism from here to here, but I believe it. But okay, that's why I'll say this is kind of a sketch still. Then what? Then we know that this dimension here is the same as this dimension, and this dimension here is the same as this dimension. So this tells us that the dimensions are the same. Omega JY is HI omega JY log. Okay, so these two things here. Okay, so this will tell us at each stage that these will tell us that these have the same. These are actually equal. These are two numbers, and they're the same. So this injectivity. Okay, so we did it at stage 1. So and then now we have the dimension counts that are the same. So then so this tells us that so back to the case J is equal to 1. So what did we get? So at the end of the day, we got that HI Y omega 1Y. This is isomorphic to. We had this injective map, and now that we know that this injective map is bijection. Okay, and then so the Bloch-Kato lemma, part 2. So this thing tells us that that what? this tells us that the next stage, we get the next stage of vanishing, I, y, omega 2y. Okay, and then you repeat this procedure. Okay, so then you repeat this process, and this will eventually tell you that the whole thing is 0. And so I guess the whole part is that relies on a couple things. So you're using that, you know, just kind of like that these dimensions are the same, and that you have actually an interpretation of P rank in terms of this. Okay, and since it's the dimension, so the hypothesis said that it's a dimension, so we have that these two things are the same. Okay. Yeah, the key thing was this Bloch-Kato lemma. Okay. So thanks for watching. So let's prove that P rank ordinarity. So this is saying that a Abelian variety has maximal P rank is the same thing as this Bloch-Kato definition of ordinarity in terms of vanishing of the cohomology of the boundaries. So the strategy is as follows. So strategy slash proof here is okay. So let's suppose let's suppose that for all I, hi y bj is equal to 0. So we're gonna fix some j. We're gonna fix some j, and then we're gonna apply a proof. Okay. So the first thing that we're gonna need to show is that here I'm gonna call this heart. Let's say, and this there's one thing. So this is, well, I'll call it heart. Okay. This thing is hi omega j. So these logarithmic differentials here, this is this, okay, is equal to hi omega j here, like so. And then the second thing that we're going to need to show is injectivity. Well, and the injectivity will follow from just the Bloch-Kato. So we'll have hi omega j y log here. This is from the Bloch-Kato, the first part of the Bloch-Kato lemma. I omega j here. So from this hypothesis, we get this injectivity. So this is for i's and j's. Okay, and so if we have this and we have this, so we have an injection and they're the same dimension, this will imply that here this omega j log is isomorphic to hi omega jy. So like that. Okay, so if we have this isomorphism, then the second part of the Bloch-Kato, so this is implied by the second part of the Bloch-Kato lemma. This tells us that, so this is really from Hart in the first part of the Bloch-Kato lemma. It tells us that hi y b j plus 1 is equal to 0. Okay, so this is how we go from this step here. So we suppose here, so we at some fixed level. Okay, once we have that, well, we get this first part for free. This injectivity of this map that's from the Bloch-Kato lemma, and then if we can show that we have an injective map and that they're the same dimension, then we get this isomorphism here. Okay, that's the idea. I need to take care of this, and then and I think that's that in the base case, and then we're done. Okay, so so let's look at this. So the base case. So the base case is really follows from the P rank lemmas. So we have that the P rank. So from here, the P rank here. So this is from the P rank lemmas. we said that this is h0, 1, y log, like this. And then we also have here that this is equal to h0 omega 1 y log. Here, so this is, oh sorry, this is this. So this is just, this is by hypothesis. By hypothesis of maximal p rank. Of maximal p rank. P rank. For so for ordinary varieties, right? Abelian varieties. Okay, so we have this base case. So we have these two are the same. That takes care of this here in the base case. And then we need to actually show this one here too. So here. This one is actually silly. Let me just say why we have for all I. So we have for all I, hi, y b 0 is equal to 0. This is the stupid. So this is a stupid sheaf. This is just 0, right? And so when you take the cohomology of something 0, that's 0, and that we get that for free. The last thing that we need to check is that that this heart thing holds at each level. Okay, so let's check that heart holds at each level. So how do we do this? Well, to do this, we simply just use some cohomology here. So H just is just cohomology of abelian varieties, Jy. So this is isomorphic to HIYO tensor with H0Y omega JY, like this. And this part here is the ith wedge power of H1. So, and this can be found in Mumford's book on abelian varieties. Omega 1. Okay, so this is cool. Okay, so we have this dimension here. Similarly, we're going to have that HIY omega JY, and then we do it with log. So this is the same thing. I'm going to break this up the same way. Y omega j y log. Okay, and now this is the ith wedge power. Okay, and then we have the jth wedge power, h0y omega 1 y log. Okay, so now we have these two things are we can break them down, and it really reduces to this and this. And so by hypothesis, the base case here, we have that these two things are the same, right? They're the same. So these two things being the same will imply that these two are the same as well. Okay, so we conclude, therefore, that HIY omega JY is equal to HIY omega JY log. Okay, for all I and j. Okay, this is assuming the p rank. Okay, so again, let me just say this again. So what was the strategy? So the strategy was here. We start at some level. Okay, and we have this Bloch-Kato lemma that says if we have this condition, this map's injective. If we have an injective map, it suffices to show that it's a bijection by doing this. And why do we want to show it's a bijection? We want to show it's a bijection because we can apply the next part of the Bloch-Kato lemma, which says this top piece here, which says that this is vanishing. And that brings us to back to the hypothesis of the original thing. And then we kind of feed this into the same thing. Okay, so we feed it into itself, and it's an inductive proof. Okay, and so that's how p-rank ordinarity implies Bloch-Kato ordinarity.